All right, welcome to The Explainer. You've probably heard about the quantum internet, right? This future network that's supposed to be super powerful, super secure. But there's a catch. The signal it runs on, it's incredibly fragile. So today, we're going to look at a really clever fix for one of the biggest glitches holding the whole thing back. Okay, first things first, we got to talk about the secret sauce, the magic ingredient behind this whole quantum internet thing, entanglement. So picture this. You've got two tiny particles, say two photons, and they are quantumly linked. It's like they're connected by an invisible thread. Whatever you do to one, the other one instantly mirrors it. And I mean instantly, even if they're on opposite sides of the universe. It's that wild, spooky connection that's the key to everything. And this quantum link, man, it opens the door to some seriously mind-bending tech. I'm talking about communication that's literally unhackable. Why? Because if anyone tries to eavesdrop, they break that fragile entanglement and boom, you know instantly. We're also looking at teleporting information. Now, hold on. Not people, sorry, but the pure quantum state of a particle. And then there's something called super dense coding, which is just a fancy way of saying we can cram way more data into every single signal. So, okay, scientists are working like crazy to build this quantum superhighway. But to really get the most out of it, to carry all that data we were just talking about, they realized they needed a better signal, a serious upgrade. And that upgrade has a pretty cool name, hyperentanglement. Think of it like this. Regular entanglement links just one property of two particles, like, say, their polarization, which is just the direction their light wave wiggles. Hyperentanglement, though, it links multiple properties all at once. So now you can link their polarization and the path they're traveling on, which is called their spatial mode. It is literally like going from a fuzzy standard def TV signal to crystal clear 4K HD. You can just pack so much more information in there. But, and you knew there was a but, right? Here's the catch. This super powerful, high-def signal, it's also super fragile. And like any good story, this one has a villain. See, as these little photons are zipping down fiber optic cables or even just flying through the air, they bump into things. They interact with the world around them. And all that interaction is, well, it's noise. It's like static on your car radio. It just messes up that perfect quantum signal, ruining the connection. And for this whole quantum internet thing to work, that signal has to show up in perfect condition. No static allowed. So what do you do? How do you fight all that noise? Well, for a long time, the main game plan was something called entanglement purification. The name kind of says it all. It's about trying to filter out a pure signal from a messy, noisy batch. So here's how the old way worked. You start with a ton of these entangled pairs that have been beat up by noise. Then you run a bunch of tests to find the few that are still in good shape, the ones with a strong link. You keep those. But here's the crazy part. You throw away everything else. I mean, everything. It's exactly like tossing a whole bag of groceries because you found one bruised apple. Just so wasteful. And this is a huge problem, right? This process is just ridiculously inefficient. Think about it. A lot of those pairs you're throwing out might have one good part left. Remember, we're talking about hyperentanglement, multiple properties. Maybe the polarization is messed up, but the spatial mode is still perfect. But nope, in the trash it goes. And that wastefulness, it was a major, major roadblock. Which leads us right to the breakthrough in this paper. The researchers basically looked at this situation and asked a simple question. Wait a minute, what if we could save some of those pairs? What if we could rescue the good parts from the not-so-good ones? And that's exactly what they did. They came up with a really smart new trick to be way less wasteful when cleaning up the quantum signal. It's called the quantum state joining method, or QSJM for short. And honestly, the best way to think about it is quantum recycling. It's a genius way to take two damaged pairs and stitch their good parts together to make one perfect pair. Okay, let me walk you through how this works. Let's say you have one pair of photons. Its polarization link is great, but its spatial mode got scrambled by noise. Then you have a second pair, and it's the total opposite. The polarization is junk, but the spatial mode is pristine. Now, under the old system, both of those pairs would have been tossed out, gone. But with this new method, this is where the magic happens. The QSJM lets scientists basically cut and paste. They can take the good polarization from that first pair and join it with the good spatial mode from the second pair. And what do you get? One perfect, high-fidelity, hyper-entangled pair made from two pieces of so-called junk. That's not just recycling, that's upcycling. Okay, so this all sounds great in theory, but does this quantum recycling actually work in the real world? Does it really make a difference? Well, let's take a look at the results. And the results are, well, they're not just a little better, they're dramatic. I mean, look at this chart. It shows the efficiency, pretty much your odds of successfully making a pure, high-quality pair. That lower bar, that's the old way. And that much, much higher bar, that's the new method. By saving all those states that used to be thrown away, the improvement is just huge. You don't have to take my word for it. The authors themselves put it best. They basically said, look, this thing is way more efficient, and that's exactly what we need to build the kind of long-distance, high-capacity quantum internet we've all been dreaming about. So what's the bottom line here? It's simple, really. By figuring out how to recycle these quantum states, this research makes building a quantum internet a lot more practical. It's less wasteful, it's faster, and it solves one of the biggest efficiency headaches that was holding everything back. This is a really big step forward. Yeah, this work is a huge leap in making the quantum internet a real thing. And it leaves me with one final question for you to think about. As we keep getting better at protecting this incredibly delicate information, what's the first thing it's going to change for you personally? Will it be totally secure banking, a whole new kind of computer on your desk? Or is it going to be something none of us have even thought of yet? It's pretty wild to think about.